So you've learned about KSP, the solubility product constant for a dissociation reaction. It's unique from the normal K values because, of course, K here has no reactants, right? They're just one, they're a solid. So what we get is a product, right? A product concentration, ion concentration equation, all right, and expression. All right. And so you previously got walked through 3 ice table problems that go with equilibrium. And now we're looking at the specific case of solubility product constant. And you should have gotten through 2 out of the 3 analogous types of problems. So for this one, practice problem, calculate the solubility from KSP. What did you get? You probably had to start by writing the balanced chemical equation for the dissociation process and equilibrium of the solid, which would have been, let's see if I can get my pages correct. Where am I at? All right. I feel like I'm, here it is. You should have gotten that silver chloride, and I'm assuming this is silver 1, AgCl. That tends to be far more common. Don't know why they didn't specify. Solid goes back and forth between Ag plus aqueous and chlorine ion aqueous. And so what you get is, given the KSP, what do you get for the KSP value in the table? You had to use the table. Okay, so KSP from the table is 1.8 times 10 to the negative 10. And again, it's a no unit, just like any normal K. And what it tells us, by the way, is the KSP is just a fancy way of saying not a ratio between product and reactant, but straight up how much ion concentration we have. Like that's basically the explanation of it. KSP is all about how much ion concentration do I have. If I have very little ion concentration, that means I have very little dissociation, which means I have a very low soluble or near insoluble ionic compound. Yes.
So this is insoluble?
This is very low soluble. Like there's technically some, right? You do technically have like a microscopic, what is that?
Would that be solid if it's low soluble?
Well, it's low soluble means it prefers to stay as a solid. Yes. But there's,
wouldn't we have a precipitate if it's that low soluble?
You do have a precipitate. AgCl is going back and forth. So the equilibrium based on the KSP is way in favor of the reverse for solid and way little dissociation forward. That's kind of what it translates to.
What is the KSP when one of the ions is a solid?
Then none of the ions would be a solid for KSP because it's dissociation.
Like say AgCl turns into silver solid and then
it doesn't, because it's dissociation of an ionic compound in water. Like it is dissociating. Like this is not a chemical reaction. This is a physical process. All right. So then what you should have gotten is, what was your answer? If you use the method from above where you put, here, let me highlight this, move it over. Okay. Oh, gee willikers. Where you said that ice table essentially, right? S. Okay, this becomes non-important. Okay, the change is going to be, well, actually the change is SS and it starts off as, theoretically 0, 0, right? SS. And you get that your equilibrium values are then SS. So you get that your KSP is equal to S squared. So KSP equal to S squared. What do you get for S? And S represents molar solubility here, just to differentiate the uniqueness of this particular KSP problem. This is the maximum amount of ions present in solution measured in molarity. That's hence S. Okay. And you should have gotten a value of what?
1.3 times 10 to the negative 5.
Perfect. 1.3 times 10 to the negative 5 molarity of each ion is present, right? Each ion is present. So that is what you should have gotten. If anyone didn't get that, we unfortunately do not have time to go over it a ton. but I highly recommend the AP problem videos. They're gonna really help you. Yeah. So I spend a lot of time editing those and remaking them each year if there's an error. So I hope that they are useful. All right, next one. It's the same process except for the fact that I want you to report not in molarity, but in grams per milliliter. So again, you would have started with the balanced chemical equation. So iron, okay, oops, G will occurs. Iron 2 sulfide. So that's an FeS solid dissociates in equilibrium process or reversible reaction process of to Fe2 plus aqueous and sulfide to minus aqueous. And you would have set it up. You would have found that the KSP is what? What is the KSP according to your table? 6.0 times 10 to the negative 19th, which again tells you that we are way, way, way in favor of the reverse, keeping the solid, and very not much in favor of the forward dissociation process. Okay. And what you should have gotten is, again, you would have gotten the setup that it was equal to S squared, because this is, if you were to do the table, right, you would have gotten SS as your change, and stoichiometrically speaking, it is a 1-to-1 ratio of ion to reactant. So you would have gone SS as your equilibrium. So S squared. So what was your S then for this problem? 7.7 times 10 to the negative 10 molarity, right? Because that's what we're in, is molar solubility value. So then what you need to do is you would have needed to convert to grams per milliliter. So times, molar mass of grams over moles times milliliters, 1,000 milliliters per liter. And you should have gotten then a value of your solubility, not in terms of molarity, but in terms of grams per milliliter, which would have given you the answer of 6.8 times 10 to the negative 11 grams per milliliter solubility for the particular dissociation of iron sulfide.
Would it be 1,000 milliliters per liter or 1 liter per 1,000 milliliters?
Thank you. Thank you so much. I flipped it. I appreciate that. Yes, you are totally right, Jay. 1 liter for 1,000. Thank you. Okay, so
Wait, Ms. G,
yes.
why do we use these big KSP tables instead of just big molarity tables?
What do you mean? Why do we use these big KSP tables?
Having the value of the solubility in molarity just seems like a more useful statistic to have.
It is, but we can't do it without the KSP relationship.
But why do you get these tables full of KSPs? Why not just like store the big table as the molarity data?
Oh. So like basically just say for this particular dissociation, this is the molarity of each ion. Because what if the molarity changes?
How would the molarity change?
I create a different concentration of the ionic compound.
Maximum molarity.
But if I'm a different concentration, if I have a 0.5 molar sample, right? Like it's not standardized enough. It's not standardized enough. So it's for this particular molar sample of this ionic compound, we get this saturated molarity level. But if I change the volume it's in, or I change the amount of mole solute of ionic compound, it changes the molarity value respective to that context. But the KSP never changes because it's the product of the relationship, stoichiometrically speaking.
How would changing those factors change the molarity? Because it looks like molarity is entirely based on KSP.
Yeah, how would the moles per liter change if you just like added moles per liter? Add moles per liter to start.
Actually, they're right, because there is a certain molarity at which it is saturated, and that doesn't change. The only way that concentration actually affects KSP is if you calculate KSP from an unsaturated solution.
Hold on,
But
it
yeah,
keeps.
you're right, you could just tabularize
Do you know why?
the molar concentration.
Wait, repeat what you said about the concentration while I try to get this thing back up.
Molar molar solubility is also standard to a compound at a specific temperature. It does not change, and having a different.
But
amount-
KSP is subject to change because it is subject to change in concentration. That's the whole point about why KSP is unique, is because without the ratio, we cannot say that it is consistent. That is the concept from the textbook, that what makes KSP different is that it is subjective to change to concentration. For the first time, the K value for this particular situation is impacted by the concentration. So therefore, you cannot conclude that that is a standardized enough value.
The way I understand it, it's only impact if it's unsaturated, because that concentration, which is itself a ratio of moles per liter,
Why is it not working?
won't change. Like the concentration of.
I mean, there's literally a table on
saturated ion.
Wikipedia, just like molar solubility table of every single compound known to humans at a specific temperature for each of them.
Well, then I don't know why they don't do that. But all I know is that this is what the AP says.
Do what the AP tells you,
Alright,
Yep.
even if they're wrong.
All right. So next problem, your second type. You were asked to predict whether a precipitate was formed based off of the relationship between Q, K, and K for a KSP. So, all right. So what did you guys get for, oh, this is always a long but problem. Okay. So for this one, you were given the original milliliters of a double displacement reaction. You had to figure out what was the solid formed in your double displacement reaction, and then you had to write the dissociation for that solid. So what you should have gotten for this is that this double displacement reaction was PbNO3, 2, and 2NaIO3, sodium iodate. Okay, goes to PbIO3, 2. Okay, and this is your solid, plus 2 NaNO3. And remember, the AP likes you to memorize certain rules about solubility. Anytime you have a nitrate or an alkali in a compound, it is always soluble. Okay, so then what you would have gotten is that your dissociation is between PbIO3 in equilibrium with its respective ions, Pb2 plus, and 2 iodate ions. Okay, and so then what you would have gotten is you would have been given KSP from a table. So your KSP is equal to 3.7 times 10 to the negative 13, which is equal to your KSP expression, which is the concentration of lead times the concentration of IO3 raised to the third. Or third, sorry, I was looking at the second. All right, and oh man, you would have to do so much math. Okay, so then what you have to do is you have to figure out, okay, what is the Q value? So you have to go through ice table problem, and I'm actually going to quickly move this up so it fits a little better. Let's have you be in a different color. Okay, so then you have to do ice table problem. So this doesn't matter, right? And you know that you're going to have S and 2S. So your equilibrium values are going to be S and 2S because that's your change. And so what you get then is your KSP is going to be, oh, you know what? We don't have K here though. We're not told we're at equilibrium. So what we're told is we're at Q. So our Q expression is going to be S times 2S squared. Okay, because we're not told we're at equilibrium. So we're trying to figure out
like S times 2S squared.
Because it mimics, it's the same setup as your K in terms of concentration. So the concentration of PB would be S, and the concentration of IO3, oh, sorry, minus iodate would be 2S squared.
But they have
Because-
different concentrations.
Huh?
They have different concentrations.
Yes, yeah, well, they would have stoichiometrically be related in their concentration. So whatever amount of PbIO3 actually dissociates, it will produce a stoichiometric ratio, set ratio of the following ions. So you know that whatever change happens in Pb2 plus, however many Pb2 plus ions you get from dissociation, you're gonna have twice that many ions of IO3. So-
You apply the equilibrium ratio as well as the molar or stoichiometric.
Yes, yes. You apply both.
Squared times S.
Yes, you apply both. And here's the interesting thing is you use the equilibrium process, but you are not at equilibrium. So here, S doesn't, does S represent molar solubility at saturation level? I don't know. That actually might be part of the reason that we can't do it. Is because if we put it in Q, does it, I don't know if we can plate that. I don't want to get back into that. The point is that, okay, you have 4S cubed. Okay. You do have a given amount of original concentration. So 8.5 milliliters times 6.3 times 10 to the negative 2 molarity gives me an initial molarity of what for my PbIO3 2? What was the initial molarity for PbIO3 at the beginning?
PbIO3
Mm-hmm.
is
Base.
6.3 times 10 to the negative 2.
So this was a 6.3 times 10 to the negative 2 molarity.
Well, but no, you start with lead nitrate and you go to sodium. We don't have the concentration set.
So we had to find the concentration. So what was your diluted molarity for each one? Because, oh yeah, so because you have two, yeah, you have to count for dilution in each of these. Man, this was a nasty problem. Okay, so you had to count for the dilution of PbNO3. All right, to figure out what was the concentration of Pb in your dissociation, Pb2 plus, okay? So what did we get for the diluted concentration of PbNO3 2 after mixture? And then we need the diluted concentration of NaIO3 to give us the source of IO3. I'm just gonna get rid of this because I don't think we even fully need this. Let's get rid of this. I don't even think we need this table. Because we're gonna get actual data, so we can just plug into Q. We don't even need the table. We can just get actual data. It is a hard Monday. Very little sleep this weekend does not help. Do you have the diluted concentration by chance?
I have the which concentration of lead?
Oh, okay. Of lead nitrate?
No, lead.
But what was the lead nitrate value that you originally got? It should be the same. theoretically, because for every one lead nitrate, you get one lead.
Okay, I have 5.3 times 10 to the negative fourth mole per liter.
5.3 times 10 to the negative fourth molarity, which is going to be multiplied by a 1-to-1 ratio of Pb2 plus and 1 Pb NO3 2. You're going to get that the molarity of Pb is 5.3 times 10 to the negative fourth molarity Pb2 plus. And that's going to go here. 5.3 times 10 to the negative fourth molarity. Okay, for the sodium iodate, what did you get for diluted? (1.19 times 10 to the negative 3 molarity. And for every not quite yet. So for every one IO3, or sorry, one sodium iodate, you get one IO3. So you see here again that we have a molarity of IO3, which is 1.19 times 10 to the negative 3 molarity for IO3 minus. So you do, the original amount was 1.19 times 10 to the negative 3, okay? Or actually, sorry, the amount in solution is mixture is 1.19 times 10 to the negative 3. Now, these are your current molarity values at any point in the reaction. We don't know if it's equilibrium, and we're trying to predict, well, if we're being told that we have to predict if precipitate will form, we're being told that we aren't at equilibrium, and we're going to find a new equilibrium, and whether that transition to equilibrium or that journey toward equilibrium favors the precipitate, or the reverse reaction is what we're going to determine. So we do then that Q is equal to same expression as K. All right, it's the same expression as K. But this time we put in the values that we do know. So what did you get when you put in the values of 5.3 times 10 to the negative fourth times 1.19 times 10 to the negative 3 squared? What'd you guys get? Yes.
Isn't the 1.19 also multiplied by 2? Or is it 4 cubed or s times 2 s?
Yes. Yes, it is. Yes. There's a reason. You're like, why is she thinking about this? There's a reason why I'm thinking about this, because there are other problems where you don't have to change it. But this is, I think you are correct. So if you multiplied 1.19 times 2, so I'm just going to do that, 1.19 times 10 to the negative 3, multiplied it by 2. All right. What do you get for your value? And then you square that, whatever that value is. 2 point, what? 2.38? Oh, okay. I was like, that cannot be correct. 2.38 times 10 to the negative 3. I was like, oh my God, that's so wrong. Okay, perfect. Perfect. And then what do you guys get for Q? 13. What'd you say? 3.05 times 10 to the negative 9. So what we see here is that Q is greater than K. So when we compare, Q is greater than K, which means that we have way more products of ions. We have way more ions in solution than what should be at equilibrium. So we are going to definitely favor precipitate formation, because we're going to try to reduce our ion. Does that make sense? All that work for that answer.
I feel like this is a great place for some.
Yes. So that's that table. They'll give it to you. They will always give it to you unless the problem is to solve for it. But if you need it for a problem, they will give it to you. Okay. Yes.
Why did we multiply the iodine concentration by P?
Oh my God. Sorry. I apologize. So- because there were 2 iodates necessary for the solid. So in the provision, the source molecule of the iodate only provided 1 iodate, but we would have had to get 2 iodates to make the solid PbIO3, 2 of them. So
What was the point of the Q equals S times 2S squared?
that was me in my brain. That was not
So
necessary.
you didn't use that at all?
Well, you used it conceptually, you just didn't need to use it written. Because like you set up the actual concentration expression using that same ratio of for however the change was comparable. Okay. So let me see if I can get my shared content back up. Sorry guys, I'm also very, very tired from this weekend, and I am not someone that manages very well under exhaustion. So I do apologize. I know a lot of this is on me right now. Okay. So let's see if it'll transition to Notability. Yay. Okay. Sometimes it freezes. Yeah, it's been charging.
Thanks.
You're welcome.
Sorry, I have to do an interview today. I didn't realize that my
Oh.
computer wasn't charged.
No worries. All right. So let's do the third type of KSP problem, which is analogous to the third type of ice table problem. Here, we're going to calculate ion concentration from KSP. And this honestly, it's just a lot of math. It's just annoying, but it's not too hard. So here we have what mass of sodium sulfate is required to start precipitation in 500 milliliters of 0.03 calcium chloride. Assume volume remains constant. So first and foremost, you have a double displacement reaction. You need to identify what the precipitate is. So when you write out the double displacement reaction and balance it, you would get that you get calcium sulfate as your solid from this double displacement reaction. Then you would say that the calcium sulfate undergoes a reversible dissociation of the solid and produces calcium 2 plus and sulfate 2 minus. Okay. And then what you would get is you would have to find KSP, and you know that KSP is from the table. So you would find that KSP is 7.1 times 10 to the negative 5th, which is going to be equal to the concentration of calcium 2 plus multiplied by the concentration of sulfate 2 minus, and it's a 1-to-1 ratio. So you leave the exponential values as 1. Okay, then what you would see is that you have to calculate, just like above, what was the source of your calcium, okay, given the original ionic compound it came from. So from this ionic compound, calcium chloride, we're told that we have a concentration of 0.03 molar calcium chloride, which is going to give us a concentration of calcium in a 1-to-1. So the concentration of calcium is 0.03. Sulfate, on the other hand, we are told that we are going to get it from sodium sulfate. And we don't know what that is, actually. Well, that's what we're going to try to solve for. This is our X. We don't know what that is. Okay. So what we have is we do know that we can solve for the concentration of sulfate now that we have one of the concentrations of our KSP expression. Okay. So we say to ourselves, well, if KSP is 7.1 times 10 to the negative 5th, and it's equal to 0.03, the concentration of calcium. Here, we didn't have to deal with dilution because they told us volume stayed constant, times whatever our X value is, which is our unknown SO4 2 minus. Okay, so we solve for SO4 2 minus, and we say that the concentration of SO4 2 minus is equal to 2.4 times 10 to the negative 3 molarity. That is what must be true at equilibrium. This is the amount of ions that should be present after the double displacement reaction and the slight dissociation of the solid produced, the precipitate. So now what we're asked though is what was the mass of the sodium sulfate originally required? And we also have to account for that it's in a particular volume. So we say to ourselves, well, we need to figure out what is the mole amount in a sample of, okay, 500 milliliters of this particular molarity, okay? So, and I'm just gonna actually make this a different color so it shows the different steps. So what then must the mole be? Not times, but equals some amount of mole value over 0.5 liters, which is, by the way, the 500 milliliters. That will tell me the mole value of sodium sulfate.
0.5 liters over some mole value.
Well, right now I'm just saying it's equal to that.
Oh,
Yeah. So that will give me not the concentration of the sulfate in the sodium sulfate. Okay. And what we get then is we get the value of, I have a molarity value of SO4 2 minus as 1.2 times 10 to the negative third moles, okay, of SO4 2 minus is required to have this particular equilibrium concentration of this particular ion in this particular amount of volume. But I'm asked what the mass is. So now that I have moles, now I use my molar mass, okay, to calculate my amount of sodium sulfate. And things that you have to remember is sodium sulfate has a 1-to-1 ratio of sulfate ion. So what I can say is for every 1 sulfate ion, and actually I should write like this, 1 sulfate ion, I have 1 sodium sulfate. So I multiply that times 1.2 times 10 to the negative 3 moles of sulfate. And that gives me the moles of sodium sulfate. And then I multiply that by the molar mass of sodium sulfate. And so the molar mass of sodium sulfate is some value. I don't feel the need to multiply this out for you, of sodium sulfate. And that would give me an overall value in grams of 0.17 grams of sodium sulfate was required initially. Yes. No. I mean, it would change your molar mass value, but I didn't write that in. Yeah. So. Okay. Go ahead and try the next one on your own. All right, for this problem, I totally forgot. This problem required me to tell you that this was calcium sulfate that is being mixed with calcium carbonate. You know what? Let's just skip this. It's unnecessary. I think I'm going to cancel this one for next year as well. I don't like this example, and I forgot to make a note of it from last year. Somehow that slipped past me when I was redoing the notes. So let's just actually move on from that. And because that actually requires you to know to the following right here, which is common ion effect. That problem requires you to know the next thing. So let's just move on to the next thing. That marks the end of the 3 types of KSP problems that are analogous to the 3 types of ice table problems for general K. All right. The most annoying part about the KSP problems is all of this dilution stuff. That's the really annoying part, and that you have to first identify the precipitate, which means you have to know your solubility rules to identify what's the solid that will undergo reversible dissociation. Okay. So it's kind of just additional steps that's really annoying. But once you get to the point where you're using K expression, it's the same as any other problem. And it's actually, in a sense, less work because you're not using the ice table at this point. Now you're just using your generic stoichiometric ratios. Okay. But common ion effect, which this problem actually introduces, next year canceled. I'm going to remind myself to take that out of the notes next year. Common ion effect is when, in particular with dissociation, so we're still under KSP scenarios, dissociation, we have, okay, when, or it occurs when a solute okay, a solute solubility, solutes, okay, solubility is negatively impacted by the presence of a shared ion in solution, i.e. the solvent shares an ion. So what that means is it's kind of like saying if you have a reaction equilibrium, A goes to B and C, and you're in a solution where your solvent has a bunch of C, what does that do to your equilibrium? Additional C will drive the reaction backwards. So what that means is that your normally relatively soluble precipitate becomes less soluble in the presence of a solvent with a shared ion, because that Le Chatelier's principle, LCP, Le Chatelier's principle tells you that increase in solute concentration contributed from the solvent is going to destabilize or create a new equilibrium shift in the actual dissociation of your focused solid. Does that make sense? Okay. So, consider a saturated solution of AgCl. How can you change the KSP for AgCl? Well, according to the textbook, and I'm just going to kind of leave it at that, you can change it, okay, through temp and concentration. Please don't argue about that with me. It is what the AP asked you to know. It is on AP questions, okay?
What if this K is small, it's just temperature?
If the K is not for a dissociation problem and it still has your ratio of a reactant under a product, it is just temp. KSP is the only K value that has a response to concentration. So that means we could change the Ag concentration or the Cl concentration, and it would create a new KSP value for the same compound. All right. You can also want to consider how you can change the solubility then. Well, according to, again, Le Chatelier's principle, you can use a solvent that already has that shares the Ag ion or chlorine ion. And what will happen is, again, according to Le Chatelier's principle, it will cause a shift in equilibrium and therefore favored reaction, right? Rate of forward versus rate of backwards in the equilibrium position, AKA a shift in dissociation, right? It'll cause a change in the dissociation magnitude or the amount of dissociation. So how do we then calculate the solubility with a common ion? This is a fun problem. So let's say I have MgOH2 and it's in water. Standardly, we would use our common setup where we do KSP is equal to table. We'd get the value of 5.6 times 10 to the negative 12. Which is going to be equal to the concentration of my ions produced, Mg2 plus, and OH minus squared, because I have 2 OH ions produced for every 1 MgOH dissociated. So I write out my little equilibrium. Okay, I get S and 2S, which means that my KSP is going to, you could also say it's equal to, right? 4S cubed. So you solve for S, and S becomes, when you solve for S using the KSP value, you get that S is equal to 1.1 times 10 to the negative fourth molarity. That would be in water. That would be basic unshared ions. Okay. Now, if you're like, water has an OH, yeah, but water neutralizes itself. So it's a 1-to-1. It just neutralizes itself. So we're fine. Water has essentially no impact at room temperature. You can technically have acidic water at different temperatures, and you can have basic water at different temperatures, but we'll talk about that later. Okay. But what if you are now in the presence of a solution that shares the magnesium ion, MgCl2? So an MgCl2 solution or solvent will shift it. Now what's going to happen is we're going to see that, okay, logically speaking, that the dissociation is going to become less favored. We already know then, logically speaking, according to LCP, the dissociation or the forward reaction will become less favored. So we're going to create more precipitate, or we're going to keep our solid as a precipitate. So then what we see is that we have to set up an ice table. And here we're going to go back to ice tables. And we're going to say, okay, well, according to my reaction of MgOH, two of them, forming Mg2 plus and 2OH minus, my ice table would tell me that I have, when I initially drop in my MgOH2, okay, doesn't matter because it's a solid, but I do initially have, instead of saying 0, 0 ions, my solvent provides me 0.10 molar ions, because for every 1 MgCl2, I have 1 Mg2 plus. So my concentration, as soon as I drop my solid in, is already at a dissociated value of 0.10 magnesium 2 plus ions provided by the solvent alone. None of the solid has dissociated yet. Okay. Then that means that, all right, that means that what's going to happen is I'm going to theoretically have more Mg with the slight dissociation from my solid added to my initial amount of Mg2 plus from my solvent. And I'm going to have the stoichiometric addition of 2x OH minus, and that would give me an equilibrium value of Mg2 plus as 0.1 plus x and 2x for OH minus, hydroxide ion. Now, the truth of the matter is looking at the KSP, this is a very low KSP. The low KSP indicates to us that there is minimal, okay, Mg2 plus ion contribution from Mg, table, Mg, yeah. So with that super low KSP value, we know that the change that would occur from MgOH2 dissociating is almost negligible. Like, it's compared to your massive amount of solvent molecules, solvent ions, you basically have no contribution. So what we actually do is we treat this as negligible. The addition of Mg2 plus from the compound is negligible. But we do say that the addition of the OH minus is significant because there's no other thing to outcompete it. So we do have to account for that. Okay. And then what we get is then we get this following relationship, that KSP in this particular solvent is going to be equal to the value of 5.6 times 10 to the negative 12, which is going to be equal to the equilibrium concentration of magnesium, which we're going to say is approximately 0.1, considering the other contribution from the actual solid to be negligible, times the ion concentration of our hydroxide, which is 2x, and then it's going to be squared. So we do account for both the stoichiometry and both the stoichiometry between the ions and the stoichiometry in the full reaction. And we get then that when you set this relationship equal to 5.6 times 10 to the negative 12, we get that x is equal to 3.7 times 10 to the negative 6 molarity. And that x is, all right, the solubility, molar solubility of our respective species. And that is how you would determine what the solubility is in the two different solvents. Yes.
Say, where's the threshold for treating X as negligible?
The threshold is if you are in a common ion problem, you can pretty much treat the shared ion source from the dissociating solid as negligible. That's just the assumption that in a common ion problem where the solvent is obviously in magnitude larger amount, the AP gives you problems where you just assume that you can treat it negligible.
Is there any problem with not treating it as negligible?
That you will find new problems in different contexts, but not for this context. As soon as it's a common ion problem, you can just bank on that.
But if you weren't to do that, would it mess everything up, or would you?
You would just have to, you'd have to account for the X there. It would just make math more complicated. You would get a comparable value. It would just be more accurate and require a lot more precision in the math. All right, try the next one on your own. Yeah, go ahead and try the next one on your own. Okay, so for this problem, this is another common ion problem, and you're told that you have this compound, silver iodate, and you want to figure out what its solubility is in molarity, given that it's in a solvent of sodium iodate. So the sodium iodate, okay, shares the common ion of iodate. So what you have to recognize is that when you're trying to calculate the molar solubility of silver iodate, you have a Le Chatelier equilibrium problem, and that present iodate increases the concentration of iodate in the overall solution, driving the reaction backwards. So what you're going to want to do then is you're going to want to account for this. So you know that you have a 0.12 molarity of sodium iodate solvent. For every sodium iodate, okay, you get one iodate ion. So it's a 1-to-1 ratio of iodate. Oh God, for every one sodium iodate. So you know then that you're going to plug in 0.12 molarity, okay, for the initial concentration of your iodate. And it would be 0, solid, doesn't matter. Now you say to yourself, okay, well, stoichiometrically speaking, for every Ag ion produced from the dissociation of my silver iodate, I am also going to get a change of positive X amount in a 1-to-1 ratio. Okay, so then that means my equilibrium values are X and 0.12 plus X. But again, if you look at the KSP, okay, and they pretty much always give you KSP values where you can apply this assumption, which was what Liam was asking me earlier. It is 3.2 times 10 to the negative 8th for silver iodate, which is still really low. Like that is a low KSP value, which means that this will be negligible. The contribution of your actual solid giving you some iodate is basically like insignificant compared to the solvent's contribution. It's going to be times 10 to the 8th tiny amount added. But our solvent provides in the second digit place of a decimal. I know, I also am praying right now too. So, what we're going to say then is since that's negligible, okay, we're going to say, okay, so that means we can calculate.
Adding the point, well, so.
0.12, yeah.
With a 0.12, yeah. 0.12 comes from the fact that we have, 0.12 molar
Mhm.
sodium iodate.
Yes, it comes from the solvent's molarity.
So we're taking the iodate
From the solvent.
that and putting it into the silver iodate.
And we're putting it into the iodate concentration present in solution as a free floating ion. Remember,
So we're-
dissociation is the result of a solid just breaking up into its individual ions.
Well, wouldn't it be more, because since we're adding.
What do you mean more?
We'd have more iodate than 0.12.
Yeah, but it's such a negligible amount of more because look at our KSP value. It's in the times 10 to the -8. It is so not favorable for this compound to dissociate anyway. And then you add in a whole bunch of one ion, it's gonna basically be like, nah. But it will, however, create a relatively significant amount of Ag plus because there is no Ag already in solution. So we do have to account for the fact that there is an additional Ag going from 0 to something, even though it's small. So what we say then is then we estimate that the KSP is equal to X times 0.12. And we get then that X, our molar solubility in this common ion, is 2.7 times 10 to the -7 molarity. Okay? So we can do a similar conceptual breakdown on pH. Okay, no, I cannot answer your question. We need to finish this.
It's very, very quick. I did the including the negligible amount. I got 2.607. So pretty close.
Okay, perfect. So we got it confirmed from Malcolm. So pH is another kind of effect because remember pH is a measure of H plus ion. So when we say pH as a affectant of solubility, you got to remember that pH really stands for H plus or OH minus ions present. So it's really, again, a common ion solution type of problem, just being represented by a different macroscopic property. And I realize I have not looked at all of the side of the room for the entire hour. Okay, so pH and solubility. All right, this is the last thing. For a weak acid or weak base, okay, for a weak acid / weak base ionic compound, okay, that demo or have low solubility, okay, pH can affect solubility. pH affects the solubility. For a strong acid, strong base, this is not so much the case really at all. Okay, but the pH of your solvent will affect it. So here's just more of a conceptual walkthrough, okay? Let's say you have zinc hydroxide and it has a KSP of this. This is a really low soluble based off of this KSP, 10 to the -17. This guy does not want to dissociate like at all, okay? But it will bit, okay? In pure water, you get the following process. And I'm okay with just showing you this picture because you've already been through this process multiple times. You would get that the solubility of this zinc hydroxide compound when dropped into water would be 2.2 times 10 to the -6. But here's the problem. What would happen to the solubility if you were to change the pH? Put it in a more acidic solution, okay? Well, if you're producing OH minus, all right, to put it in a more acidic solution means that your OH minus is going to be neutralized by your acid. So your OH minus is going to be neutralized by your acid. So what's going to happen is that we remove OH minus in reaction due to side neutralization reaction, thus resulting in our dissociation, okay, to favor ion formation, okay? Or to favor the forward, to
Wait,
say,
why is it 8.6 for a non-7?
it's saying that, I'm just saying, like, what if I put it in a more acidic solution, such as, oh, because it's the original pH of this solution is 8.64. So what if we made it into a more acidic solution? Yeah. Favoring ion formation, therefore the forward. So what we would see is, according to Le Chatelier's principle, you would see a major shift, an increase in solubility, right? So this would be an increase in solubility. Solubility increases. Okay, the opposite would be true for below. What if you put this particular more basic compound into a more basic solvent? Okay, well, what happens is you would have, it'd be like adding OH minus, okay, causing the reaction to shift toward reactant or precipitate. Okay, causing the reactant to shift toward reactant or precipitate, therefore decreasing solubility. Okay, and so then what if we considered this with a sample of H plus? Now, instead of having an ionic compound that produces, okay, OH, now we have H plus, and we're gonna warm up with this question tomorrow. Okay, we're gonna warm up with you putting this together tomorrow. And that is all I have for you today. And good work, you guys. We are so close to spring break. It is so close. Please get your unit 6 AP problems done so I can allow all of you to do corrections with full credit back. I think it'd be very good for you. You do have an AP problem to go through tonight, so best of luck.